Assalamualaikum warahmatullahi wabarakatuh. So today my group will present about the turbine driven generator. My group consists of 3 members, which is Muhammad Daniel Mukri bin Zulkifli, Ahmad Daniel bin Abdul Manaf, and me, Haziq Ashraf bin Adam Hussein. So now we are looking for the introduction for the project. The turbine drive, often referred to as the driven train, is a crucial subsystem that connects the turbine rotor to the generator. It is designed to manage the efficiency transfer the mechanical energy generated by the turbine rotor to the generator. The key component of the driven train include the rotor, blade, and hub assembly. The blades are carefully engineered to capture the energy from the fluid such as water, air, steam, or gas and convert it into the rotational motion. In systems like wind turbine, the rotor rotates at a low speed with high torque due to the large aerodynamic force exerted by the wind. Now we look at the objective. The objective is split into 3 parts, which is efficient energy conversion, reliable electricity output, integration across energy system. So efficient energy conversion maximize the conversion of mechanical energy into electrical energy with minimal energy losses. How about the reliable electricity output? It deliver consistent high quality power to homes, business and industry. Integration across energy system, which is support renewable and non-renewable energy sources for diversification and sustainability.
So we will go to the next slide. So before we go further, let me introduce myself. So my name is Muhammad Daniel Mukri bin Zulkifli. So today I gonna introduce or explain about our circuit diagram, which is the turbine drive generator. So based on the slide, we can see we have a basic turbine driven generator, which is we have the turbine itself, and then we have a circuit as a generator, and then we have the storage battery where the electrical energy has been stored. So we go to the next slide, which is we can see this is the circuit that we simulate that we using the multi-sim. You can also using another app such as the MATLAB, but for now we're using the multi-sim. So if you can see, we have the watt meter and then we have the ammeter. So we have a few components here. We have the voltage supplies in AC mode, which is the voltage is 230 VRMS with the frequency 50 Hz. And then we have 3 passive components, which is we have the inductor with 0.1 Henry, we have the capacitance which is 20 microfarad, and then we have the resistor with 100 ohm. So we can see after we run the circuit, we have the current total is 3.191 ampere, and then the power actually is 528.615 watt, and then the power factor, which is the main topic for the assignment, actually here is 0.7202. So for the next slide, actually we do some basic calculation to prove our simulation actually in the right track. So if you can see here, we collect all the data that we have, which is we have the V equal to 230, we have the frequency 50 Hz, we have the resistor, inductor and capacitor. So before we start to calculate the current total and so on, we need to change the inductor and capacitor into the inductance reactance and capacitance reactance. So first of all, here I do the inductance reactance, which is SL. So the formula actually SL equal to 2 pi FL, and then you just fill in all the formula, and then we got the J 31.416 ohm. So next we do the capacitance reactance, which is SL equal to 1 over 2 pi FC, and then we fill all the formula, and then we get the negative J 159.155 ohm. So from here we can see the difference between inductance reactance and capacitance reactance. So actually the difference between both of the reactance, actually the J itself, J actually stand for the imaginary. So for the inductance actually is a positive, while capacitance is negative. Why? Because actually the inductance introduce the phase lead of positive 90 phase, while for the capacitance actually it's the capacitor introduce a phase lag of negative 90 degree. So actually it's not, this is important, so but it's not affect so much for the answer, just memorize it. So for inductance it will be positive J and the capacitance will be negative J. So that next we calculate the total impedance, just sum up all the impedance, and then we find the magnitude of the total impedance, which is the impedance total. We using the parallel formula, because if we can see on the previous slide, we can see actually the inductance and capacitance connect series, and both of the component connects parallel with the resistance. So the magnitude Z total we got is 78.74 ohms. So from that Z total we can find the total current. We using the Ohm's law, which is V equal to I Z, and then if we want to find the current total, V over the Z, and then we will get the total current is 2.991 ampere. So from that we can find the phase angle. So the formula for phase angle, actually phase equal to upturn the current through LC divided by the current through resistor. So we calculate the LC also using the Ohm's law, and then we got the current to LC is 1.8005 ampere, and then the current at the resistor we get is 2.3 ampere. So from that we fill all the formula, and then we got the phase angle is 38.055 degree. So from that phase angle we can find the power factor, which is a power factor equal to cos theta, and then we will get the power factor is 0.7874. So if we compare from calculation and the simulation, yes, I can say that it's not exactly same, but the result is actually close to each other. If we can see the current total from the simulation is 3.191, while the calculation is 2.991. So actually it's close. Maybe in terms of calculation we skip the decimal number, and then we just shortcut here and there, and the result will be slightly different, but I can say that actually our simulation was in the right track. So next, if we can see actually in the assignment, the assignment assigned us to correct the power factor. So the power factor previous is 0.7, right? So we need to change, we need to decrease the power factor to make it the power factor become unity. What is unity power factor? So unity power factor, actually you make the power factor become 1. The number is 1 lah. So after try and error, some here and there, we change the capacitance value. So if we want to increase the power factor value, we need to decrease the capacitance value actually. So for the next slide, we can see we decrease the capacitance value from 20 microfarad to 1 microfarad. So another things we simulate, and then we got the total current actually 2.303 ampere, and then the power factor, which is the main actor right now, actually we got 0.99949. So we also do the calculation method to prove. So from the calculation, we just do the same thing from the previous calculation, and then from that we can prove that actually our calculation and our simulation are linked. And then we do some calculation, just the same step with the previous calculation. We just calculate, and then we can say that our simulation was right, because the theoretical, which is the calculation, and the simulation was the same answer. So from here we can conclude actually by decreasing the capacitor value, we are reducing the circuit overall reactive power, and then improving the alignment between voltage and current, leading to an increased power factor. This is a key principle of the power factor correction, where capacitors are carefully sized to counteract inductive effect without overcompensating.
Assalamualaikum, my name is Ahmadina bin Abdul Manaf. Today I want to talk about discussion and conclusion. The discussion is the analysis begin with a circuit simulation before power factor correction characterized by a low power factor approximately 0.72020. The high current supply of 7.65 ampere indicate inefficiencies in energy usage resulting in increased losses. Theoretically, simulated calculation confirm each branch initial values for power and current. Power factor correction was achieved by introducing a capacitor into the circuit, effectively reducing the supply current to approximately increasing the power factor to near unity 0.99949. The comparison table demonstrates significant improvement in system efficiency, validating the theoretical approach and simulation outcomes. The conclusion is the study highlight the critical role of power factor correction in enhancing circuit efficiency. Simulation confirmed a marked improvement in power factor from 0.7020 to 0.99949 with a corresponding reduction in supply current. This minimized energy losses and aligned with best practices for sustainable energy usage. The theoretical and simulated data align closely, reinforcing the reliability of the proposed correction. Future studies could explore real-world implementation and impact of varying capacitor values on performance.